Today, Yuval and I will talk about ongoing work. Hope to have it public soon, like in 2 weeks or 3 weeks on ISCR. It's the Laurent Stark, sister of the Circus Stark, and that's what this talk gonna be about. So, yeah, it's about M31 again, another Stark over M31. We know it, beautiful for CPU, fast CPU arithmetics. But what's the main caveat? Not FFT friendly. And there's a line of work that makes it useful for Starks, though it's not FFT friendly. The first one was the early paper of Daniel Lubarov, Jackie Nabaglio, and I, which I will describe in the following slide in detail. It had its caveats. Mainly for those who are familiar with it, it was constraint evaluation that was not really satisfying. But it laid the path to the Circus Stark. So that was like last summer when Shahar Papini was approaching me and saying, hey, look, we can do the ECFD or the Circle, can we? And yeah, we investigated it, and that accumulated in the Circus Stark, which has native performance, though it's not an FFT-friendly field, thanks to this kind of novel, or let's say this type of algebraic FFT you run over the circle, which is similar to the elliptic curve FFT. And the third thing, oh, nice, that's nice. I think we do it without Tango, no? Nice. We can talk about identifying your keyboard. Okay. Oh, thanks. Okay, and yeah, next one in the row of works over M31 was actually the RC Stark, the really complex Stark of Yuval. I'm not sure how many are familiar with that piece of work. I, to be frank, largely ignored it. For reasons, because I knew that you can use harmonic FFTs to do the Circle FFT, so I thought, and I was in contact with Yuval, he will run into the same troubles as we did in the first work, the problem of constraint evaluation, so I didn't take it fully serious. Turns out, funnily, we met at ZK Proof, and I promised, oh, it's on my list, it's on my list. I will look at it, I will look at it. This time, really, and I did. And funnily, it's a solution. It patches the gap the first work had. Is there something like, yes, the first work had. So this one patches, can be seen as the completion. It completes the path that was taken in the very first publication. It does so in a very elegant way. And we will see that this RC Stark, which is content of the Stark, surprise, surprise, is a nice sister of the Circus Stark, useful. So concretely, the write-up that we're going to publish will formalize the ST Stark. We give it a better name. We'll call it Laurent Stark for reasons we will see in a second. And more importantly, it describes the relation, the geometry. What does the Laurent Stark have to do? What does the RC Stark have to do with the Circus Stark? And the takeaway of it was quite surprising for me. Though it's not difficult, I'm not saying anything is difficult here, but surprising that actually it brings not just insight to see both Starks working over the same manifold, but it also gives practical insights. In particular, I will talk about two improvements that gives the Circus Stark more flexibility if you learn from the Laurent Stark. Okay, so let's start with the early approach of Jackie, Daniel, and my paper, the Ritz-Solomon code over the circle curve. So what we observed, and I'm sure probably we were not probably the only ones, but you know, M31 Q minus 1 is worst case two-adic. There's only one factor 2 in, not even a second one, 1 power of 2. But that means that there does not exist a square root of rho unity of -1. So what you can do is introduce it like stepping from the real to the complex numbers in calculus, define your element that is the square root of -1, and construct the Gaussian integers. And over this quadratic extension, what's nice is, if you look at the unit circle in the complex plane, that this is exactly, first of all, it's a cyclic subgroup, cyclic multiplicative subgroup, and its order is exactly q plus 1, Mersenne prime plus 1, which is a power of 2, and that's nice. So what you can do over that is then, okay, we are in the complex, we can do the complex FFT, but in order not to pay the price for the complex extension, we do packing, and that leads to reasonable performance in FFT as if it was native over the base field FQ. Moreover, use the FFT, you interpolate by polynomials. These polynomials, as we will see later on in further slides, they will have conjugate, their spectrum, their list of coefficients will have certain symmetries. And these symmetries are useful to further improve, because FFT is just one part. You pay when you go to an extension field. The other part is commit. So the key observation in the early work was, although, let me step back for a second. So we interpolate by polynomials which have complex coefficients, but they have certain symmetry, that if we evaluate over a coset of the subgroup H where we started from, then these values are almost real again. So this is the coset evaluation. We just need one factor, one normalization, which depends on the shift factor of the coset to make it real. That means over the base field again. And we called that back then to rectify the values, the coset values. One coset, 8 times H, just one factor to rectify the entire vector of coset evaluation. We called it rectified with Solomon code, and we were happy. We said green lights for M31, let's do the Stark that way. But when thinking about implementation, there was a caveat. This kind of representation, this rectified representation, you can see P of AZ is, if you just bring this to the other side, you can say this is something like the angle, and this is the radius. It's something like polar coordinates in the complex plane. And that's good polar coordinates for multiplication. It's also okay for addition if they have the same angle. But if not, then you leave the realm of rectifiable representation. That means if you do constrained evaluation, you sooner or later end up with complex representation because you cannot efficiently represent it anymore over an entire coset in a rectified manner. And that's a caveat which is nasty. Maybe not a showstopper, but in the end, the enthusiasm about this approach declined. Okay, but then there was the circus Stark and so on, you know this story. And then comes Yuval last autumn, and he say, wait, I mean, this rectification thing, look at this. Just view it as the nature when you evaluate a Laurent polynomial. What's a Laurent polynomial? It's just like a polynomial, but now we have also negative powers of z. And let's say a Laurent polynomial of degree n goes from z to the n minus n over 2, which is the highest negative power, to c to the n plus n over 2. Yeah, just view it as Laurent polynomials. And that's what the Laurent Stark or a C Stark is about. And it's now time for your show.
Thanks, Ulrich. Okay, so quickly I'll show you what the Laurent Starks are. I'll try and tell a story a bit of how I got to it. So they're actually a simpler stack over M31. They've got the regular FFT. IOP is nearly the same, as you will see, just with these new Laurent polynomials, and then Frey and all, new types of Frey, stir, and were, they're very, very similar to what you're already used to, and it's nearly as performant. We will see that as well. So if we look at, these two polynomials, they're the same. The first one is basically just a Laurent polynomial of degree n, okay? And we take coefficients that are conjugate symmetric. The middle coefficient is real. If we take that over the circle, so we set z to be, exponent of I theta, then we see that this polynomial, it's the same polynomial, we can actually just manipulate it a bit, and then we get to these trigonometric functions, where all the coefficients here are just the real parts of the complex coefficients, and that's why the evaluations are always real. It's an n plus 1 dimensions polynomial. It's real valued over the unit circle. When you get off the unit circle, it's defined, but it's not real valued. And this we'll skip for now. Now, that space of Laurent polynomials, of the real ones, we call Ln, the n plus 1 dimensional space. And we want to look at another space, a subspace of that space, an n-dimensional subspace, where the edge coefficients, right, the n over 2, are actually equal. N over 2 and minus n over 2. And obviously, if they're equal and conjugate symmetric, then you realize that they need to be real as well. And this was my initial thinking. So this is the story. You take just a sequence of length n, and you do the FFT of it, or the discrete Fourier transform of it. Here I took n equals 8. And you straight away see this symmetry, right? But there's like one annoying coefficient, the first one, that seems to be out of place. So what do you actually do with it? And I was thinking, how do you actually do like a low degree extension of these things so that it stays real? Well, when you think about it, because this is a Fourier transform, you're over the unit circle, you can actually just do these periodic extensions, and actually, it doesn't matter if I take like z to the power 4, it's the same as z to the power minus 4. And then we just define a different set of the same coefficients that are equivalent over the unit circle. And notice that we take also the middle coefficient and we split it into 2. Now we get this nice symmetry. And that's actually the Laurent polynomial, okay? So you see that it spans n plus 1 coefficients, but it's actually an n-dimensional space. The coefficient, the edge coefficient is really like the same degree of freedom. And this straight away leads to the way that we do low degree extension. So if you look at the top, within this dotted square, that's the result that you will get from an inverse DFT. And then if you look at the solid lines, that's how you would look at it as a Laurent polynomial. And then that straight away says, how do we zero pad it? We actually push everything apart. The zeros go on the two edges of the Laurent polynomial. And then we can straight away do a DFT, and we'll get the new real evaluations of the extended code. Okay, now quickly, everything from now works the same, just with Laurent polynomials. So if we look at the n plus 1 space, the n plus 1 space has closure for addition and also for multiplication with the usual times 2 length extension, but that also works for the n-dimensional space. Vanishing polynomial, we have the usual z to the n minus 1, but we need to actually shift it. And if you note, we also need to multiply it by, it's actually imaginary, so that it's actually in the n+1 space. It's not in the subspace. Selector polynomials are simple. All different types of error constraints, like single point ones, out of domain, rep. It all works out of the box, the same as you're used to. Fry, stir, whir. It really depends on how many coefficients we have. If we're doing quotients, then all we need to do is just shift the polynomial by n/2. So now we have a usual univariate polynomial, and that's the reduction. Now we can do the usual Fry. If we have n+1 coefficients, then we do this trick where we shift it and then get rid of the constant coefficient. So in practice, for the Fourier transform, right, to get it fast, we do packing, and we do this split radix implementation. And then the cost is nearly the same as what we're used to. It's actually n/2 log n multiplications, and instead of n log 2 additions, it's 1.5 n log 2 additions. So it's very close to the circle FFT, and it's close actually to the usual entity that you're used to. So now I'm going to hand it back to Ulrich to give you the geometric view.
Okay, so we saw, I mean, for those who are familiar with the Circle-Stark, they probably noticed already some similarities in the Laurent-Stark, like the FFT space. The image of the FFT is n-dimensional, as large as the domain, but the entire space, the natural space of Laurent polynomials of the same degree is one more, right? That happens also in the Circle-Stark. And also the removal of that one coefficient that we had in order to apply Ver, that's also something that occurs in the quotient decomposition of the Circle-Stark and so on. But okay, forget about this for a second. The geometric view. So let's go back to the circle. That's how it looks like over M31. You know, in the plane, it's a planar. It's a planar affine curve. We can touch it. We know it, how it works. Yeah, but the better view on the circle is actually that's like always in algebraic geometry. You go from the real numbers in analysis to the complex number to the algebraic completion, and there you see the true characteristic of the manifold. And when you step over to the quadratic to the complex extension, actually the circle curve looks like this. It's a bit a cheat of that picture because the formula is x squared plus y squared equal to 1. So we're still in the two-dimensional complex or four-dimensional real space. We have a surface, two-dimensional surface in the four-dimensional real space, but it turns out that actually you can isomorphically map it to really the unit sphere in the three-dimensional space. So the point is, whereas the ordinary circle, there are no points at infinity. But if you see the complete picture of the complex numbers, there are 2 points at infinity. One is that pole, and the other one will be that pole in that, let's say, in that model. Okay, and the way you typically achieve it, the canonical way, that's also used in the Circle-Stark paper. It's not an invention of the Circle-Stark, just used. The canonical way to achieve that image is first of all, look just at the circle in the plane. Fix one center of your stereographic projection. Then take any other point, take the line that is spanned by the two, and see where it intersects a fixed plane that you choose for the projection. And in that way, if you move now that second point along the circle, you see that you will end up, you will get the real line, right? You will get a line in the plane. And also, if you take now if you now move out, or let's rewind. So that's actually, it looks like this in a formula. If you really choose specific normalization, it looks like a very simple fractional expression for that stereographic projection. And that expression makes sense in the extension of in the four-dimensional real space, even if you don't understand, can't think about 4 dimensions, you know. And the thing is, if you look at the image, then you will see that the 2 points at infinity, they will be mapped to plus and minus imaginary unit. And if what's not in that picture, if you think about the orbits of a point on the under rotation group that keeps the 2 points at infinity fixed, you will see also circles here. They're not concentric, but they're circles. And the thing is, you just see that parametrization, that complex one-dimensional description of the curve, and it reminds you on the stereographic projection of a classical in the 3D space, that surface. So that is how you obtain that picture that I was said in the beginning is a bit cheating, right? So, but that's a good way to think about the circle curve. That is where the circle Stark happens. And okay, funny thing is, there are different ways to parameterize the circle curve. And it turns out actually, if you use the trivial embedding that used the very first work, that means you just have the real description of the complex unit circle. You take 2 points of the real unit circle and map it to x plus minus iy. That's not a complex unit circle. That this just as in algebraic mapping extends also to the full circle curve. And in that view, it's just a different stereographic projection. You choose the center to be not something that is on the real curve as before. You now choose it here, one of the poles. And what happens then? Fix that as the center. Choose 1 point of the real circle curve. That stays fixed because it's already, if you choose now the xy plane as the projection plane, so that stays fixed. And everything that is in the lower half of that, what's the right word, of the sphere is mapped at the inner of the curve. The other pole is mapped to 0. And the more the upper half of it is mapped to the outside. And at its extreme value, if you approach now the center, you get infinity of the projective line here. You get the infinity. So the funny thing is here, the 2 points of the circle curve, the 2 exceptional points at infinity, are mapped now to 0. And this is a different infinity. This is now the projective complex plane. Okay. So why is that interesting to look at where these exceptional points at infinity go to? Because 0 and infinity, let's just go to the Laurent polynomial. Powers of 1 over z and powers of ordinary z to the 1, where do they have poles? Z to the 1 has only pole at infinity. 1 over z has only pole at 0. So 0 and infinity, that's the defining pole set for those from algebraic geometry. That's the support of the divisor for the Riemann-Roch space. So that's the defining pole set for Laurent polynomials. Likewise, the regular circle polynomials, they only have poles at infinity, at the 2 points of infinity. This is the defining set for the circle polynomials. And that means that this specific identification, this other type of stereographic projection, this maps the Laurent poly on the circle polys. It's even degree preserving. That means Laurent polynomial of degree n are mapped to a circle polynomial of degree n over 2. And the FFT space, which was named, I think, still Ln plus in Yuval's part, that corresponds to what is, that's why we named it Ln plus there, because in the circle, over the circle curve, we deal with 2 spaces, essentially Ln plus and Ln minus. One is Ln minus is the circle FFT image, and Ln plus is just the rotated part of it. So the thing is, the FFT space of the harmonic regular FFT equals a rotated circle FFT space. Okay, let's wrap it up. So first of all, Laurent Stark is a circle Stark just with a different FFT and therefore a different phi. So what's the takeaway here? We see that we can, I mean, besides that it's a simpler and has a Stark and has reasonable performance, we can improve that caveat of the harmonic FFT, that overhead in addition, but just implementing, using the circle FFT for faster Laurent encoding. So it can be improved. Costs, of course, a bit of work. On the other hand, and that's the surprising thing to me, is that the Laurent representation is very interesting for the circle Stark itself. In particular, there are black box reduction. You just make a Laurent polynomial into a regular polynomial. And then you run phi, or you run stir, or you run ver. It doesn't matter. That means you can use black box, the security analysis of it. You don't have to pull it over to the circle, which is possible. We know it works, but it still works to write it down. So you can immediately apply stir and ver out of the box. That's nice. The other thing is that STU is a flat, uses flat airs. That means no transitional constraints from row to row. It's the design principle most modern ZK-VM implementation go along, like OpenVM or Binius. So over the circle, it's surprisingly difficult to come up with the analog on the univariate subject that doesn't work with running sums. But with Laurent polynomial, it's easy again. So you can pull it over to the circle, or arbitrary set interpolation. So like in data availability sample, you have a non-group structured set, you want to have the interpolating polynomial over it. That's, to be fast here, you need something like the monomial basis, which behaves nicely under the derivative, but the circle basis doesn't. Again, the Laurent representation of circle polys is a good solution here. Okay, that's essentially it.